The Moscow Popular Science Film Studio presents Man and the Atom. On the 1st of March, 1896, the French scientist Henri Becquerel was working in his photo laboratory. He was about to develop a photographic plate on which several crystals of uranium salt had accidentally been lying for several days. Scenario by Ostromov. Directed by Dombrovsky. Camera by Klementiev, Utochkin, Artseulova, and Azov. Sound by Beknazarov. We don't know what the scientist thought when he first saw the traces of the action of nuclear forces. But could he have imagined And what if Henri Becquerel had accidentally broken the plate? It would be naive to think that science would not have harnessed the energy of the atom. If not Becquerel, it would have been someone else. The forces of nature by themselves are neither good nor bad. It depends on man to direct them in the proper direction. A few years after Hiroshima, scientists from many countries gathered in Geneva to discuss the problems of the peaceful use of atomic energy. Here at the exhibition, the leading countries demonstrated what wonderful things the atom is capable of doing in the service of peace. The spirit of Geneva is the spirit of cooperation. Everyone in Geneva in those days could see and appraise the upsurge of scientific thought, the newest developments of atomic technology so necessary for the future. Dr. Bhabha, the Indian physicist, had calculated that within the coming decade, humanity will be faced with an energy hunger. Who knows? It may be that when this boy is 40, his country will have burnt its last piece of coal and last drop of oil. Professor Dolezhal of the Soviet Union and physicist Dr. Zinn of the United States are discussing the details of a Soviet nuclear reactor. Nuclear power engineering is capable of generating electricity, heat and light for all the people of the world, for every single one of us. The dwellers of distant forests and the inhabitants of big cities get their energy and consume it in different ways. Concern for obtaining energy has never slackened throughout human history, from the Stone Age to the atomic age. Yes, the age of the atom has begun. We can mark the hour of this age from the moment the doors of the world's first atomic power station in the Soviet Union opened. The atom is able to help human progress for hundreds of years, but to do so, it must be under control of the hand that regulates the reactor of a nuclear power station.
Down scope.
And not the hand on the trigger of a Polaris atomic submarine.
Ready?
Ready.
5, 4, 3, 2, 1, 0, fire.
Will the atom destroy human beings, or will it help to heal them? We know that the able atom is capable of healing. But what are they doing here? Building a road? Or a house? Or a town in the desert? No. They're making preparations for testing a new atomic bomb. All these structures are needed for the sole purpose of finding out how they'll fly to pieces in an atomic explosion. Here's another test. and another. These are only tests with no casualties. Yes, there are no casualties. Only rain, radioactive rain. Its droplets seep into the future. Young mothers give birth to deformed children. Or children like these. Will the atom serve good or evil? All of them were children on the fateful day of Hiroshima. Forbid nuclear weapons. Forbid the testing of such weapons, says Hewlett Johnson, Dean of Canterbury.
Mercy, brotherhood, and peace here and not in some distant realm, now and not in some far-off time.
Soviet writer Ilya Ehrenberg says, it is not of our own fate that we are concerned. We hold ourselves responsible for all children, white and dark. All children, white and colored. For the children of London and of Moscow, of Paris and Peking. For the children that live near the skyscrapers of New York and of those that wander among the ruins of Korea. We shoulder the responsibility for all the young in love, for all the books of the world, for all the cities and all the gardens. Worried people ask, is there really going to be another war? Is it possible to live in such an unsettled state? Is it possible to bring up children and wonder when the bomb will fall? Can we think, can we create and advance human culture when the specter of war hangs ever above us? It's impossible, and we cannot allow it, says Joliot-Curie. We cannot allow humanity to perish from the forces that man's reason and hands created. Human hands are skilled and deft. For thousands of years, they fashioned vessels out of clay. For hundreds of years, they painted them with this bright color, never suspecting that it contained uranium, the very same uranium that Henri Becquerel experimented with. Of the many elements that exist in nature, a few are found in the pure state. Iron, sulfur, gold. The others occur only in compounds. The apparent chaos of elements was first overcome by Dmitri Mendeleev, who discerned order and a strict dependence of the properties on their atomic weights. Mendeleev's periodic table of elements opened the way to a fresh upsurge of the natural sciences towards the end of the last century. The age of iron. The age of steam and electricity. During those years, physicists were more and more concerned with problems of electromagnetism. The foundation was being laid for the future edifice of science. Stoletov had already investigated the photoelectric effect. Hertz had discovered radio waves, and Popov's first radio set was working. Thomson observed the deflection of a beam of electrons in a magnetic field. Studying the luminescence of cathode ray tubes, Röntgen discovered the mysterious X-rays that were fated to save so many human lives. At that time, at the turn of the century, nobody even suspected the dangers that lay hidden in such radiations. This is a page from Marie Curie's notebook. To this day, it bears the traces of radioactivity. It speaks of the selflessness of a great woman who devoted her life to the atom. From old snapshots and documents, we follow the persistent search that immortalized the names of Pierre and Marie Curie. We repeat the historic experiment with the modern tools of radiochemical experimentation. Marie Curie continued the work begun by her teacher Henri Becquerel. She presumed that the radiation he had discovered was not due to uranium, but to an unknown substance contained in the uranium ore. Hundreds, even thousands of kilograms of ore were broken up, dissolved, and evaporated. Day by day, week after week, from month into month, the work went on, pouring out, evaporating, adding fresh solution, and again evaporating. The same thing over and over again. Every evening, in the dark of her laboratory, Marie Curie noticed an increasingly bright glow from the solution. Almost 4 years of unimaginably hard work in order to obtain a tiny quantity, 1/10 of a gram, of this strange substance. In December 1898, the Curies, husband and wife, published an unpretentious report presented by Becquerel. We succeeded in isolating a new substance to which we decided to give the name radium. Radium took its place in the Mendeleev periodic table. It differed from all known elements. Radium emitted light and heat, and emitted them constantly without any interruption. It would appear that energy was being generated out of nothing. Very soon, radium was found to produce biologic effects, but Marie Curie found this too late. Every page of the notebook speaks of a great mind and a great heart, of one who stood at the cradle of the awakening atom. But Marie herself perished in the fire that she lighted for the people. The start of the 20th century was marked by yet another revolutionary discovery. In the capital of Switzerland, at the Swiss Patent Office, there worked just an ordinary man. He was Albert Einstein. The theory of relativity that Einstein created shook to the very foundations the magnificent edifice of classical physics and yielded utterly new concepts about space and time, mass and energy. Strange and unusual in the extreme were the conclusions from his equations. The mass of a body and the energy are equivalent and can turn into each other. This accounted for the mysterious radiation of radium and demonstrated for the first time the gigantic reserves of energy hidden within the atom. Vladimir Lenin lived in Switzerland during the same period. He was working on the philosophical problems of science and was writing his famous book, Materialism and Imperial Criticism. This work became a solid philosophical foundation for modern science. The entire subsequent development of physics confirmed the amazing perspicacity of Lenin's ideas. The electron is just as inexhaustible as the atom. Lenin's idea penetrated into the depths of matter at a time when only the roughest conceptions concerning the atom were being worked out. At the start of the century, English universities continued the radioactive studies begun by Marie Curie. The baton of discoveries passed to Rutherford. He proposed one of the first models of the atom, electrons revolving about the nucleus like planets round the sun. One of his pupils, young Niels Bohr of Denmark, discovered the laws that govern the life of the atom. Bohr's ideas served as the foundation for all subsequent atomic physics. In 1919, it was again Rutherford who irradiated nitrogen with alpha particles. He succeeded in transforming nitrogen atoms into atoms of oxygen. The assault on the atomic nucleus was begun. What was happening here in Russia in those years? Hunger, war, a blockade, and still, even in such trying years, a group of Soviet physicists were at work in the Physico-Technical Institute of Petrograd. Alongside the famous Abram Yoffe were young scientists. Like Professor Lepunsky and Professor Kurchatov. In 1934, Leningrad was the headquarters of an international conference devoted to the problem of artificial fission of the atomic nucleus. Among the participants was the young French physicist Frédéric Joliot-Curie. He described his experiments with the recently discovered elementary particle called the neutron. The neutron turned out to be the best projectile for bombarding atomic nuclei. In that same year, another step was taken by the Italian physicist Enrico Fermi. He discovered the effect of the slowing down of neutrons. Fermi found that in most cases, fast neutrons fly right through the atomic nucleus without disturbing it. The experiments of Fermi and his pupils demonstrated that moderated or slow neutrons would interact more often with nuclei. One of Fermi's pupils, the Soviet scientist Bruno Pontecorvo, tells us how this discovery was made. It was quite by accident. Once, Eduardo Amaldi, who is now a member of the Soviet Academy of Sciences, and I, measured the radioactivity produced by neutrons in different metals. We had a very simple instrument like this one. The source of neutrons was radioberyllium, a small ampule about 1 centimeter long. It was put inside a cylinder. When we did this, we found that there were slight irregularities obtained during irradiation. Which meant that the intensity of this detector was sometimes greater, sometimes smaller. There was a slight difference. Near this instrument, there might be different objects, for instance, a lead brick, a brick, and so on. Inasmuch as it was fashionable in those days to talk only about fast neutrons that have a low probability of scattering in various objects, we at first did not pay any attention to the question of what there was close to our apparatus. But still both Amaldi and I felt that the effect was real, and so we told Fermi and Rossetti about it. They were the gods of our group at that time. Well, I can show them to you. See this queerly dressed figure? That's Rossetti, and this is Fermi. That's how the university professors are dressed for examinations. This man here is Segre, also a well-known physicist, a Nobel Prize winner. And so we had these irregularities. At first, Fermi and Rossetti were rather skeptical and did not believe in this effect very much. Then Fermi said, let's try it a different way. And in place of the old setup, Fermi proposed this. Here is the source of the neutrons, and here is the detector. The cylinder, and between them various substances, a kind of absorber like this one. We took different substances, and again we got irregularities. And when light materials were interposed, paraffin for instance, it was found that this activity increased. This was rather definite. Then Fermi said that if just a little paraffin produced such an effect, what would a large amount of paraffin produce? And we performed the following experiment. We put the source of neutrons and the detector this way. Now, in paraffin and even in water, there was a colossal intensity. The effect was very great. Well, of course, there was a lot of enthusiasm, and we made a lot of noise. And Fermi himself was noisy, too. And then he stopped the noise and said, let's go and have something to eat. Well, after lunch, we were still in the dark, of course, but Fermi, right after lunch, grasped the whole affair and gave us the explanation. This was the effect. When fast neutrons collide with a light element, like hydrogen, they are very effectively retarded. And slow neutrons have a higher probability of reacting with various substances. So we get something like a solution of slow neutrons, a solution of neutrons in water or paraffin. I must say that Fermi said, with the simplicity of a really great man, how silly of us not to have foreseen that before. And this effect is very important, mind you, not only for physics, but for technology as well. In 1938, Fermi left his laboratory in Rome and traveled to the United States. He could not live and work in conditions of fascism. Fascism in Italy, Nazism in Germany, and their bitterly hostile attitude towards everything human and towards free thought shook the best minds of these countries. Albert Einstein could not stand the darkness and left the country too. Einstein, like many other scientists of Germany and Italy, emigrated to the United States. He arrived in America when the world stood on the brink of war. At this fateful juncture, radiochemists Hahn and Strassmann, working in Berlin University, completed the experiments begun by Fermi and Joliot-Curie. They irradiated uranium with slow neutrons and succeeded in accomplishing a nuclear fission reaction, the splitting of nuclei. According to Einstein's theory, enormous quantities of energy should be released. Such was the news that Niels Bohr brought to New York. Physicists at work in the United States were worried. They appealed to the authority of Einstein. Leo Szilard arrived with the draft of a letter to Franklin Delano Roosevelt, President of the United States. It stated that as a result of scientific investigations done over the past 4 months, Curie in France, Fermi and Szilard in the United States, it's been found probable and possible that a nuclear chain reaction can be developed in a large mass of uranium. This could be the source of a tremendous quantity of energy. It is quite possible that in this way, an exceedingly powerful bomb of a new type may be produced. As far as I understand, the work conducted in America with uranium is at present being repeated in Berlin. Certain aspects of the situation apparently require vigilance and rapid action on the part of the government. Signed, Albert Einstein. Such, essentially, was the substance of the letter. Have I the right to sign it? Have we scientists the right to kill people with a force that should work only for the good of humanity? But what if Hitler gets the bomb first? Einstein's letter was delivered to Mr. Roosevelt. The President grasped the great importance of the atomic problem. The making of an atom bomb was put into the hands of the military and begun under extreme secrecy. Thousands of workers and hundreds of scientists were mobilized for the so-called Manhattan Project. The best physicists got to work in super-secret laboratories. Harold Urey, Otto Langmuir, Clinton Davison, Arthur Compton. The scientific leadership was entrusted to the young, talented physicist Robert Oppenheimer. Over all of them stood General Groves. In pre-war Soviet Russia, extensive investigations were being conducted in the field of nuclear physics. Skobeltsyn and Foch, Kurchatov and Lepunsky, all Soviet physicists, were hard at work on the problem of releasing the nuclear forces. As long ago as 1940, Soviet scientists had worked out the theory of the chain reaction of uranium fission, a theory without which it would have been impossible to obtain atomic energy. The young scientists Flerov and Petrshak made an outstanding discovery. They detected the spontaneous disintegration of uranium nuclei. The theoretical studies of Tamm, Ivanenko, and other Soviet physicists attracted the attention of scientists of other countries and the public at large. The Soviet Union well understood the importance of solving the nuclear problem. In 1940, the newspaper Izvestia wrote, "Mankind will acquire a source of energy that is millions of times greater than anything we know of today." Events in Germany during the war threatened to warrant the worst apprehensions of Einstein. Otto Hahn, Dr. Weizsäcker. Werner Heisenberg was head of the uranium project. They knew the path. By combining uranium and paraffin as moderator of neutrons, they constructed a reactor that could become a bomb. The top men of Nazi Germany, Goering, Himmler, and Keitel, closely watched the development of the uranium project. In the United States, Fermi achieved a great victory in 1942 in this concealed competition of physicists. In the Chicago laboratory, he and Szilard for the first time attained a controlled chain reaction in the fission of uranium nuclei. The first atomic reactor went into operation. This success set into motion a whole new industry that was built up solely for the bomb. General Groves hurried the scientists. Faster and faster still was Groves' demand. Faster, faster, faster. The bomb was still not ready, and Germany had collapsed. Soviet troops were in Berlin. The war was over, but General Groves still hurried. The bomb must be tested not later than July 17th. The first atomic explosion was being readied in the New Mexico desert.
30, 20, 10,
Robert Oppenheimer was to push the button.
8, 7, 6, 5, 4, 3, 2, 1, 0, fire.
The morning of the following day. In just a few hours, the conference of the victor countries was to open in Potsdam. Here, Truman significantly told Stalin about the test explosion of an atomic bomb of unheard of power. But this first attempt at atomic blackmail failed. Then Truman ordered preparations for the bombing of Japan. A commission made up of Oppenheimer, Fermi, Compton, and Lawrence drew up recommendations as to choice of target. Targets for bombing must satisfy the following requirements. They must consist largely of wooden and other structures that are readily destroyed by shock waves and subsequent fires. the chosen targets must be of considerable military and strategic significance. The foregoing implies that the target for bombardment should be a large city covering an area of 7 to 10 square kilometers. The cities that conform to these conditions are Nagasaki, Nagata, Kokura, Hiroshima. Why did it have to be done? Why was it necessary? Here is the American magazine Collier's. To intimidate the Soviet Union, to put it on its knees, to occupy. In the United States, the illusion persisted that the Soviet Union would have an atomic reactor not before 1955 or even 65. Many years have passed since the first Soviet reactor went into action. Today you can see the men who assembled it. Igor Kurchatov stood at the head of the atomic work. The Soviet physicists clearly realized that the Soviet Union had no need to intimidate the peoples, that the Soviet country was duty-bound to paralyze the nuclear blackmail of the West. Soviet nuclear power grew from year to year. An atomic reactor, an atom bomb, then the hydrogen bomb. Kurchatov said, Soviet atomic scientists, on instructions of the government, worked persistently and selflessly, first to build and then to perfect atom and hydrogen weapons, because they were well aware that a grave threat overhung the country. They realized that if we did not have such a weapon, forces would appear that would strive to bring our beautiful country to its knees. Soviet atomic scientists and engineers fulfilled their duty to their country.
перед страной советские ученые и инженеры-атомники выполнили.
Now Kurchatov could give all his strength to peaceful problems of physics. The Novovoronezh, Beloyarsk, and other large atomic power stations represent only a part of the broad program of harnessing atomic energy in the Soviet Union. Mobile atomic plants are being built for remote and hard-to-reach parts of the country. For several years now, the world's first atomic icebreaker, Lenin, has been plying the waters of the Arctic. The nuclear reactor of a power station uses only a few hundred grams of uranium every day, but generates as much power as a big hydroelectric station. Scientists look to the future. They're trying to tame thermonuclear reactions, which are virtual giants of power compared to the decay of uranium. They lie at the heart of the hydrogen bomb and serve as the source of solar energy. Many institutes of the Soviet Union are studying ways of harnessing these thermonuclear processes and bringing them under control. The main hero of all these experiments is plasma, the substance of the sun. But plasma is extremely unstable. As soon as it's produced, it disappears. When man has brought thermonuclear reactions fully under control, he'll be able to derive vast quantities of energy out of simple water, if science is guided by goodwill. And if there's an evil will? Recall how Truman demanded the making of a thermonuclear hydrogen bomb. He wanted to get his hands on this new weapon first in order to intimidate the world. Robert Oppenheimer could have headed this work on the new bomb. But after Hiroshima, he cursed his grave. Oppenheimer did not undertake the hydrogen bomb. He did not know to what point on the globe the Pentagon would send American soldiers, to Korea, to Syria, or to Vietnam. But he did know that this horrific bomb might be sent there too. Oppenheimer was removed from all secret work by order of Admiral Strauss, head of the Atomic Energy Commission. General Nichols stated the charge. He was always connected with the communists. He is a communist. The super bomb was made by physicist Teller. It's true that the forces of nature are neither good nor evil. It fully depends on man and society whether they will serve good or evil. Science should only work for good. This is what the great physicist Niels Bohr said.
In science means, first of all, to promote the common work in which we can help each other, and next, to create close friendship between the workers who are all working just for the same goal of increasing, deepening our knowledge of the nature around us.
Bohr encountered just such a unity of physicists at the Joint Institute of Nuclear Studies at Dubna, where scientists are penetrating deeper and deeper into matter.
Внимание в зале. Подается высокое напряжение на циклотрон. Внимание в зале. Подается высокое напряжение на циклотрон.
To learn about the microworld, one has to make protons collide with atomic nuclei and other particles. These pictures of particle collisions are photographed. One out of thousands of routine photos may be a discovery. In the laboratory of nuclear reactions, under corresponding member of the Academy of Sciences, Flerov, scientists are busy building artificial, extra heavy elements that do not exist in nature. The newly born elements are highly radioactive. Minute quantities of the new substance are obtained. Just a few atoms, actually. Day by day, week after week, drop by drop, radiochemists study these artificial elements. a tiny droplet of solution, and the mammoth particle accelerator, the proton synchrotron, both serve to help the scientists at Dubna penetrate deeper into the unknown. The more science wants to learn about the microworld, the more powerful must be the instruments of the investigator. The Soviet Union and all other countries of socialism are generously helping physicists to industrialize. Without these enormous machines, the most brilliant ideas would remain a pure abstraction. Will this huge machine bring to light new forces? What will these studies give to humanity? Academician Wechsler and his pupils are not plagued by the worries which haunted Einstein and oppressed Oppenheimer. They know what ideals their science serves: peaceful progress. Every 9 seconds, this accelerator ejects a powerful burst of particles. The microcosmos is full of great secrets. Nuclear reactions of unheard-of strength must be tamed to serve mankind. That's why scientists strike out into the unknown. They argue and seek advice, like these young physicists around Professor Jelepov.
Да, вот здесь много пар очень. Вероятно, тогда 5, что ли, 6. В общем, есть материал.
Вот здесь есть лишний засвет, у нас, по-видимому, из-за того, что там конец.
Да. Понятно. А вот это красиво тоже. Интересный случай. Ну, в общем, материал есть, как говорят. Можно жить.
Да. Вот. Счет это, конечно, да.
Every advance in science poses fresh problems.
Получить с помощью статистических методов, то в силу того, что этот уход имеет порядок экспоненциально малый, ваши асимптотические ряды будут условно-периодическими функциями, и решение будет колеблющимся. Никуда уходить оно не будет, а на самом деле все происходит.
This is how Professor Blokhintsev puts it. Yes, but then one asks how many problems there are left in quantum mechanics. They say that there are numberless unsolved problems left in classical mechanics. Likewise, there are no end of problems in quantum mechanics.
Вероятно, вот мы тут так думаем, что в непрерывном спектре в квантовой механике, но аналогичные проблемы.
Ну, конечно.
Perhaps academician Bogolyubov, head of the Dubna Center, is pondering one such problem this very minute. All physicists the world over need bold flights of imagination and audacious thinking. But men of science must ever bear in mind that they are responsible for all the cities, all the lovers, all the gardens, and all the children of the world. When one thinks of the future of this atomic age, one firmly believes that the pulse of humanity will beat calmly, vibrantly, and radiantly.